Picture the very fabric of space and time, not just as a backdrop to the universe, but as something alive, wrinkling, twisting, and occasionally tearing apart under forces we can barely comprehend. Among the most haunting mysteries lurking in these cosmic shadows are primordial black holes, ancient relics that might have formed mere moments after the Big Bang itself. Unlike their better-known cousins born from dying stars, these enigmatic objects could be hiding in plain sight, weighing as little as a speck of dust or as much as an entire planet. Their existence would rewrite everything we thought we knew about the infancy of the cosmos, and that's just the beginning of the story. What if I told you black holes might not be the ruthless destroyers we imagine, but instead cosmic archaeologists preserving secrets from the dawn of time? Primordial black holes could be the missing link between the universe's fiery birth and the structured galaxies we see today. Some theories suggest they might even be the invisible architects of dark matter, silently shaping the cosmos without us ever noticing. Others propose they're ticking time bombs, set to evaporate in bursts of energy that could light up the sky like fireworks. The possibilities are as thrilling as they are unnerving, and that's why we're diving deep into 30 of the most mind-bending theories about these shadowy giants. From the bizarre idea that primordial black holes could be hiding inside stars to the spine-tingling notion that they might be portals to other dimensions, this journey will take us to the edge of known physics and beyond. We'll explore how something so small could warp space-time like a bowling ball on a trampoline, why some scientists think they're raining down on us right now, and whether they could hold the key to finally unraveling the universe's greatest mysteries. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. Let's start with one of the most provocative ideas in modern cosmology. What if the invisible glue holding galaxies together isn't some exotic particle, but countless primordial black holes scattered like cosmic breadcrumbs across the universe? For decades, dark matter has been the universe's most frustrating puzzle, making up over 80% of all matter, yet refusing to reveal itself. But here's where primordial black holes enter the scene. Born in the chaos of the early universe, these tiny gravitational powerhouses could be lurking everywhere, their immense gravity tugging on stars and galaxies just like dark matter does. The beauty of this theory, it solves two mysteries at once: where dark matter comes from and what primordial black holes have been doing all this time. Think of it like walking through a pitch-black forest, feeling branches brush against you but never seeing the trees. Primordial black holes could be those unseen trees so dense and compact that light sails right past them, leaving no trace except their gravitational pull. Some might weigh less than an asteroid, others as much as a mountain, but their combined effect could explain why galaxies spin faster than they should, and why the cosmos clumps together the way it does. Unlike traditional black holes, which announce their presence with glowing accretion disks or violent mergers, these ancient relics would be nearly impossible to spot directly. They'd drift through space like phantoms, occasionally bending light from distant stars or triggering ripples in space-time, clues so subtle we're only now learning how to look for them. Critics argue that if primordial black holes were this abundant, we'd have found more evidence by now. But their counterpoint is just as fascinating. What if we've been searching for dark matter in all the wrong ways? Imagine sifting sand for diamonds with a colander, you'd miss them entirely. If dark matter is really a mix of black holes spanning sizes we haven't yet probed, it would explain why decades of underground particle detectors and telescope surveys have come up empty. The irony, the very thing making these black holes perfect dark matter candidates their stealth, is what keeps them just out of reach. Yet every unexplained microlensing event, every strange gravitational wave signal, could be a whisper from these ghostly architects of the cosmos. And if we're right, it would mean the universe's greatest shadow isn't made of particles at all, but of black holes older than time itself. the universe wasn't always the vast, structured expanse we see today. It began as a seething, turbulent ocean of energy, where even the tiniest ripple could have universe-altering consequences. Picture the aftermath of the Big Bang, a time so chaotic that space itself was a roiling storm of density fluctuations. Most of these ripples smoothed out as the cosmos expanded, but some, just some, might have been intense enough to collapse under their own gravity, forming black holes in a way no star ever could. These wouldn't be the black holes we know today, born from the death throes of massive stars. No, these would be primordial, forged in the furnace of creation itself, when the universe was less than a second old. The key lies in the delicate balance between expansion and collapse. In those first fleeting moments, regions of space slightly denser than their surroundings could have crossed a critical threshold. Think of it like a cosmic game of tug-of-war, gravity pulling matter inward while the explosive force of the expanding universe tries to tear it apart. For most of the cosmos, expansion won, smoothing out the wrinkles, but in rare pockets where density spiked just enough, gravity won catastrophically. Matter and energy crumpled into points so dense not even light could escape, unlike stellar black holes, which require the collapse of a star many times the mass of our Sun. These primordial ones could have formed with the mass of a mountain or even less, packed into a space smaller than an atom. What's truly mind-bending is how different the rules were back then. Today, forming a black hole takes an unimaginable amount of mass squeezed into a tiny volume. But in the early universe, the sheer density of everything meant that even modest fluctuations could tip the scales. It's like comparing the pressure needed to crush a soda can versus collapsing an entire galaxy. The early cosmos operated on another level entirely. Some theories suggest these black holes could have formed during cosmic phase transitions, moments when the fundamental forces of nature split apart, creating shockwaves that twisted space into knots. Others propose they're relics of quantum foam, where the fabric of reality itself bubbled with microscopic black holes popping in and out of existence. But here's the catch: if these black holes exist, why haven't we seen them? The answer lies in their stealth. Unlike their stellar-born cousins, which announce themselves with blazing accretion disks or violent collisions, primordial black holes could be drifting silently through the galaxy, invisible unless they pass directly between us and a distant star. Even then, their gravitational lensing effect would be fleeting, a subtle flicker in starlight. Some might be evaporating now, thanks to Hawking radiation, fading away in bursts of energy too faint to detect. Others could be hiding in plain sight, masquerading as dark matter or even lurking inside planets, their presence betrayed only by the faintest gravitational tremors. The implications are staggering. If even a fraction of these primordial black holes survived, they'd be cosmic time capsules, preserving secrets from the universe's first moments. They could hold clues about the nature of space-time itself, or even serve as gateways to understanding quantum gravity. And if we ever find one, it would be like uncovering a fossil from the dawn of creation, a relic so ancient it predates the first stars. The hunt is on, and with every new gravitational wave detection, every unexplained flicker in the night sky, we're getting closer to answering one of cosmology's most tantalizing questions. Did the universe seed itself with black holes from the very beginning? Stephen Hawking turned our understanding of black holes upside down when he proposed something extraordinary. These cosmic vacuum cleaners might not be so permanent after all. For the tiniest primordial black holes, the very fabric of space-time could become their undoing. Here's how it works. Quantum mechanics tells us that empty space isn't really empty. Particle-antiparticle pairs constantly flicker in and out of existence like static on a cosmic radio. Normally, they annihilate each other instantly. But near a black hole's event horizon, things get weird. One particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over eons, this slow leak Hawking radiation could cause a small enough black hole to shrink, heat up, and eventually pop like a bubble in space-time. Now picture a primordial black hole with the mass of an asteroid, crammed into something smaller than a proton. According to Hawking's math, these diminutive monsters wouldn't last 14 billion years. They'd be in their death throes right now. As they evaporate, their temperature skyrockets. In their final milliseconds, they could erupt with the energy of 1,000 nuclear bombs, all packed into gamma-ray bursts lasting less than the blink of an eye. These aren't the spectacular explosions of dying stars, but something far stranger: cosmic firecrackers signaling the end of a black hole's existence. This raises a thrilling possibility. What if we've already seen these explosions without realizing it? Short gamma-ray bursts pepper the universe daily, and while most are blamed on neutron-star collisions, a handful defy explanation. Some flare too briefly or have energy signatures that don't quite fit. Could these be the last screams of evaporating primordial black holes? There's even speculation that certain mysterious deep space flashes, like the bizarre LF-bot events puzzling astronomers, might be black holes meeting their end in ways we're only beginning to imagine. The cosmic implications are staggering. If Hawking's theory holds, the universe might be littered with black hole fossils, not just the silent, invisible ones, but those in their final, violent acts of evaporation. We'd have a whole new way to hunt them, not by their gravity, but by their deaths. Some calculations suggest the final burst from a mountain mass black hole would outshine entire galaxies for a fraction of a second, packing more energy per particle than the Large Hadron Collider. It's like finding dinosaur bones by waiting for them to spontaneously combust rather than digging them up. But here's the twist: Hawking radiation gets weaker as black holes grow larger. For a stellar mass black hole, the trickle of escaping particles is so faint it would take longer than the current age of the universe to evaporate noticeably. That's why we don't see supermassive black holes leaking away. But for the smallest primordial ones, evaporation could be their defining feature, meaning the very process making them detectable might also explain why they're so rare today. It's a cosmic catch-22. The ones explosive enough to notice are also the ones disappearing fastest. This leads to profound questions about the early universe. If countless micro-black holes formed after the Big Bang, did most evaporate before the first stars even ignited? Could their collective death throes have reheated the infant cosmos, leaving an imprint we might still detect in the cosmic microwave background? Some theorists propose that these explosions might have even forged heavy elements in ways stellar nucleosynthesis can't explain. Every unexplained high-energy event in space could be a clue, a breadcrumb trail leading us back to a shadowy population of black holes quietly vanishing all around us. The hunt for these evaporating black holes is pushing our detectors to their limits. Space telescopes like Fermi scan for telltale gamma-ray signatures, while ambitious projects propose using gravitational wave detectors to catch the ripples from a black hole's final quantum spasm. It's needle in a haystack work, but the payoff would rewrite physics. Confirming Hawking radiation wouldn't just prove primordial black holes exist, it would be our first direct glimpse of quantum gravity in action, bridging Einstein's relativity with the bizarre rules of the quantum world. Every unexplained flicker in the void keeps that hope alive, whispering that somewhere out there, black holes might be dying in bursts of radiant fire. Deep in the hearts of galaxies, monsters lurk: supermassive black holes weighing millions or even billions of times more than our sun. But here's the cosmic riddle: how did these behemoths grow so enormous so quickly? The universe barely had time to form stars before these giants appeared, leaving astronomers scratching their heads. Enter primordial black holes, an elegant solution hiding in plain sight. Imagine these ancient relics not as mere cosmic leftovers, but as seeds planted in the fertile soil of the early universe, given billions of years to feast on gas, dust, and even stars until they ballooned into the supermassive titans we observe today. The genius of this theory lies in its simplicity. Normally, building a supermassive black hole from scratch takes time, lots of it. You'd need generations of stars to live, die, and collapse, then wait for their remnants to merge and slowly accumulate mass. But the math doesn't add up for the oldest quasars, bright galactic cores powered by black holes, that we see shining when the universe was less than 1 billion years old. There simply wasn't enough time for them to grow that massive through conventional means. Primordial black holes solve this timing problem by skipping the first steps. If even a few of these early black holes formed with masses hundreds or thousands of times greater than our Sun, they'd have a colossal head start. Floating in the dense, gas-rich environments of the young cosmos, they'd act like gravitational vacuum cleaners, pulling in matter at rates far exceeding anything possible today. Picture a snowball rolling downhill, growing larger with every rotation. Now replace the snow with interstellar gas and the hill with the fabric of space-time itself. A primordial black hole seed wouldn't just grow, it would feast. Gas clouds in the early universe were far denser than they are now, meaning more material was available for the taking. Computer simulations show these greedy seeds could have doubled their mass every few million years, reaching supermassive status well before the first galaxies finished forming. Some might have even cannibalized each other, merging in violent collisions that created even larger black holes, cosmic kings, sitting at the center of what would eventually become modern galaxies. This idea turns conventional wisdom on its head. We've always assumed supermassive black holes were products of their environments, growing from the remnants of early stars. But if primordial black holes seeded them, it means the cart was before the horse. The black holes came first, and galaxies assembled around them. Think of it like building a city not around a marketplace or a temple, but around a bottomless pit that inexorably draws everything toward it. The implications ripple across cosmology: galaxy formation, star birth, even the distribution of dark matter might all trace back to these initial seeds planted in the universe's infancy. The smoking gun might lie in the most distant quasars. Telescopes like the James Webb are now spotting these brilliant objects in epochs so early that standard formation theories struggle to explain them. If we find quasars powered by billion solar mass black holes existing when the universe was just 5% of its current age, the case for primordial seeds strengthens dramatically. Another clue could come from the masses of modern supermassive black holes. If they show unexpected uniformity across different galaxy types, it might suggest they all grew from similar starter seeds rather than random stellar collapses. Not all astronomers are convinced, of course. Some argue that even with a head start, primordial black holes would struggle to grow fast enough without violating known physics. Others point out that we've never definitively detected a black hole with the intermediate mass that would bridge the gap between primordial seeds and supermassive giants. But that's the beauty of this theory: it makes testable predictions. Upcoming gravitational wave detectors could spot the mergers of these mid-sized black holes, while precision measurements of quasar light might reveal fingerprints of their rapid early growth. If proven correct, this idea would rewrite galactic history. The supermassive black holes we see today, including Sagittarius, a star at the Milky Way's heart, might not be accidents of cosmic evolution, but the inevitable outcome of primordial seeds sown in the universe's first moments. It's a humbling thought. The titans ruling galaxies could be direct descendants of the very first structures to emerge from the Big Bang's chaos, their growth stories stretching across nearly 14 billion years. And if that's true, then every time we look at the center of a galaxy, we're glimpsing a relic from the dawn of time itself. Quantum mechanics and gravity have always been the belligerent neighbors of physics, constantly at odds, refusing to play by the same rules. But in the extreme conditions of the early universe, where space-time was more tangled than a ball of yarn, these two forces might have briefly called a truce. That's where quantum gravity steps in, offering wild possibilities for how primordial black holes could have formed under laws we're still struggling to understand. Take loop quantum gravity, for instance. This theory suggests space-time isn't smooth and continuous but woven from tiny, indivisible loops like pixels on a cosmic screen. In the aftermath of the Big Bang, these loops would have been stretched to their limits, creating knots of such intense curvature that space itself could have pinched off into black holes spontaneously. It's not gravity crushing matter inward, as with stellar collapse, but space-time tying itself into microscopic black hole knots. Picture a sheet of ice cracking under pressure, but instead of fractures, you get endless tiny vortexes, each a self-contained black hole born from the quantum froth of creation. String theory paints an even stranger picture. If the universe's fundamental building blocks are vibrating strings, then the early cosmos was a symphony of unimaginable energy, with strings stretching, splitting, and colliding in ways that could have birthed black holes like sparks from a forge. Some models suggest these strings could have coiled into ultra-dense configurations, their gravitational pull so concentrated that they'd punch holes right through the fabric of space-time. Unlike classical black holes, these wouldn't need to obey the usual mass limits. They could be any size, from Planck-scale specks to planet-sized behemoths, all depending on how the strings tangled in those first chaotic moments. The real mind-bender, quantum gravity, might have made black hole formation not just possible but inevitable in the early universe. Normally, you'd need matter packed incredibly densely to trigger gravitational collapse. But if quantum fluctuations could twist space-time itself into a black hole, then regions of high energy, not just high mass, might have birthed them. Imagine boiling water. Bubbles form not because you've added air, but because the chaotic motion of molecules creates voids. In the same way, the seething energy of the young cosmos could have boiled black holes into existence, no stellar collapse required. This leads to a provocative thought. Primordial black holes might not be cosmic accidents but signatures of quantum gravity's fingerprints. If we ever detect a black hole too small or too ancient to fit conventional formation theories, it could be smoking gun evidence that our current understanding of gravity is incomplete. Some models even suggest these black holes would carry distinct imprints like unique gravitational wave echoes or evaporation patterns that betray their quantum origins. It's as if each one is a tiny Rosetta Stone, holding clues to how gravity and quantum mechanics reconcile at the most fundamental level. Critics counter that without a unified theory of quantum gravity, these ideas remain speculative, and they're right. But that's precisely what makes primordial black holes such tantalizing targets. Finding them wouldn't just solve a cosmic mystery, it'd give us a front-row seat to physics beyond Einstein, beyond the Standard Model, perhaps even beyond our current imagination. Every unexplained gravitational wave chirp, every anomalous gamma-ray burst, could be a breadcrumb leading us toward the theory that finally unites quantum mechanics and gravity. And it all starts with those ancient black holes lurking in the shadows since time began. What if our universe isn't the only one, and the proof has been hiding inside black holes all along? The multiverse hypothesis, the idea that our cosmos is just one bubble in an infinite froth of universes, sounds like science fiction, but primordial black holes might be the tangible evidence we've been searching for. Imagine these ancient objects not just as relics of our own universe's birth, but as cosmic souvenirs from other realities, or even bridges between them. Think of space-time as a vast, crumpled sheet, with each fold representing a separate universe. Where these folds press together, the fabric might thin enough to puncture, creating a black hole that tunnels from one reality to another. Primordial black holes, forming in the extreme conditions of the early universe, could have been these accidental stargates, wormholes forged not by advanced civilizations, but by the raw physics of creation itself. Some theories suggest that when two infant universes collided in the multiverse's chaotic foam, the impact could have left behind black holes like scars, each containing traces of a foreign cosmos. This isn't just wild speculation. Certain branches of string theory predict that universes can bud off from one another, leaving behind black holes as umbilical remnants. These black holes wouldn't behave like the ones we're familiar with. Instead of crushing matter into a singularity, they might contain tunnels Einstein-Rosen bridges threading through higher dimensions to distant realities. The catch, crossing one would be lethal, stretched apart by tidal forces or shredded by quantum instability. But from the outside, they'd look like ordinary black holes, their true nature hidden behind event horizons. Here's where it gets eerie. If primordial black holes are multiverse artifacts, their evaporation could release more than just Hawking radiation. It might leak particles with unfamiliar properties, or even space-time signatures that don't match our universe's laws. Picture a black hole exhaling atoms that twist in impossible ways, or emit light at frequencies no star could produce. Astronomers have spotted a handful of bizarre cosmic rays with energies so high they defy explanation. Could these be fragments of other universes spat out by dying primordial black holes? Critics argue this veers into untestable fantasy, but the math holds surprising promise. Simulations of bubble universes colliding show they'd leave distinct gravitational wave imprints, ripples we might detect with next-generation observatories. Even stranger, some models suggest primordial black holes could act like cosmic radios, picking up interference from parallel realities. If certain black holes vibrate at frequencies that don't align with our universe's fundamental constants, it might hint at their extraterrestrial origins. The implications are dizzying. If even one primordial black hole bears the fingerprints of another universe, it would revolutionize our understanding of reality. These objects wouldn't just be dead ends, they'd be windows, however faint, into the infinite variety of existence. And if the multiverse is real, then every black hole we discover might carry a label reading "Made Elsewhere," silent witnesses to cosmic siblings we'll never see. The hunt isn't just about finding black holes anymore. It's about decoding their origins and whether they whisper secrets from beyond the edge of everything we know. The universe's first moments weren't just hot and dense, they were explosive in a way that defies intuition. Cosmic inflation, that brief period when space itself expanded faster than light, didn't just stretch the cosmos, it might have stretched the very fabric of reality thin enough for black holes to punch through. Picture a balloon inflating so rapidly that tiny wrinkles on its surface don't smooth out, they're magnified into deep creases. Now replace the balloon with the infant universe, and those creases with regions so dense they collapsed instantly into primordial black holes. This isn't just theoretical sleight of hand. It's one of the most compelling explanations for how these ancient objects could have formed without a single star dying. Inflation's role hinges on quantum fluctuations, microscopic ripples in energy that, under normal circumstances, would vanish without a trace. But during inflation, space stretched so quickly that these subatomic wobbles were frozen into the cosmos, blown up to astronomical scales. Most became the seeds for galaxies, but the most extreme fluctuations could have crossed a critical threshold. Gravity would have taken over, causing these overdense patches to implode directly into black holes. The math is staggering. A fluctuation spanning just a billionth of the size of a proton could, after inflation, grow massive enough to collapse under its own weight. It's like a single ripple in a pond somehow becoming a tidal wave, an effect only possible in the surreal physics of the early universe. Different inflation models predict wildly different outcomes. In chaotic inflation, where expansion occurs in erratic bursts, black hole formation might have been rare, limited to violent collisions between bubble universes. But in theories like hybrid inflation or scenarios with multiple inflattened fields, the process could have been far more prolific. Some models suggest cascades of black holes forming like beads on a string, their masses dictated by the exact moment inflation ended. Others propose that phase transitions during inflation, moments when the universe's energy state shifted abruptly, created shockwaves that crumpled space-time into black hole knots. The range is enormous, from black holes lighter than a paperclip to ones rivaling entire star clusters. The smoking gun for these theories might lie in the gravitational wave background, a faint hum of ripples from the universe's birth. If inflation-generated black holes were common, their formation would have sent tremors through space-time that should still be detectable today. Upcoming observatories like the Laser Interferometer Space Antenna could catch these whispers, revealing whether inflation was a smooth ride or a turbulent storm that birthed countless black holes. Another clue hides in the distribution of these objects. If they cluster in ways that mirror inflationary density variations rather than following galaxies, it would strongly hint at their exotic origins. Critics point out that fine-tuning problems plague some inflation models, requiring absurdly precise conditions to produce the right black hole abundances. But that's also what makes these theories so thrilling. They're testable. If we discover a population of primordial black holes with masses that align neatly with a specific inflationary scenario, it wouldn't just confirm their existence, it would give us a backstage pass to physics at energies 1 trillion times higher than any particle collider can reach. Every black hole could be a time capsule, preserving the conditions of inflation like insects trapped in amber. The implications stretch beyond cosmology. If inflation really did craft these objects, then studying them might finally answer why our universe looks the way it does, and whether it's just one of countless others born in the same inflationary fire. Fast radio bursts are some of the most enigmatic signals in the cosmos, blazingly intense radio pulses that last mere milliseconds but outshine entire galaxies. Their origins have puzzled astronomers since their discovery, with theories ranging from colliding neutron stars to alien megastructures. But here's a twist. What if these cosmic flashes are the violent handshakes between primordial black holes and the densest objects in the universe? Picture a primordial black hole, dark and ancient, drifting silently through the galaxy until it wanders too close to a neutron star. A city-sized remnant of a supernova so dense its gravity bends light into a funhouse mirror. As the black hole grazes the neutron star's crushing gravitational field, things get explosive. According to some models, the tidal forces alone could rip material from the neutron star's surface, creating a swirling maelstrom of plasma heated to billions of degrees. But here's where it gets wild. If the black hole's orbit decays, spiraling inward, the neutron star's ridiculous magnetic field could channel this chaos into a focused beam of radio energy, a burst so powerful we detect it across intergalactic distances. There's precedent for this kind of cosmic violence. When two neutron stars collide, they produce gravitational waves and bursts of radiation. But fast radio bursts don't always fit that mold. Some repeat randomly, others vanish forever after one brilliant flash. A primordial black hole interaction could explain both. A one-time FRB might occur if the black hole plunges through the neutron star like a bullet, triggering a cataclysmic discharge of energy as it disrupts the star's magnetic field. Repeating bursts could happen if the black hole gets captured in a tight orbit, periodically stripping material from the neutron star like a cosmic vampire. The math gets even stranger when you consider magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. If a primordial black hole tangled with one of these monsters, the resulting energy release could dwarf anything in our current FRB catalog. Simulations suggest the collision could twist magnetic field lines like rubber bands, snapping them back with enough force to launch relativistic jets of charged particles. These jets, interacting with surrounding gas, would produce the telltale radio chirps we observe, brief but impossibly bright. Not all astronomers are convinced, of course. Critics point out that we've never detected gravitational waves from such an event, which should theoretically accompany these encounters. but that might just mean the black holes involved are too small or the distances too vast for our current detectors to pick up. Others argue that FRB polarization patterns better match magnetar flares. Still, the allure of this theory lies in its versatility. It could explain not just FRBs but also other transient phenomena like certain gamma-ray flashes or even strange neutrino emissions. The hunt for evidence is heating up. Next-generation radio telescopes like the Square Kilometre Array will catch FRBs with unprecedented precision, possibly revealing subtle signatures like distinct frequency drifts or asymmetric burst profiles that could betray a black hole's involvement. Meanwhile, gravitational wave observatories might one day detect the faint ripples from these encounters, especially if primordial black holes cluster near galactic centers where neutron stars abound. Imagine the implications if even a fraction of FRBs trace back to these ancient black holes. It would mean the cosmos is threaded with invisible gravitational traps, occasionally lighting up when they stumble upon the wrong stellar remnant. Every unexplained radio burst could be a breadcrumb leading us to the universe's most elusive ghosts, black holes that have evaded detection since the dawn of time, revealing themselves only in fleeting, brilliant handshakes with the dead stars they disturb. The Fermi Paradox has haunted astronomers for decades. If the universe is teeming with potential for life, why does the cosmos seem so silent? One unsettling answer might be lurking in the shadows, not as alien megastructures or self-destructing civilizations, but as primordial black holes. These ancient gravitational traps could be cosmic saboteurs, silently derailing the rise of advanced life before it ever gets off the ground. Consider the hazards they'd pose to interstellar travel. A rogue primordial black hole, weighing as much as a mountain but no wider than an atom, would be virtually undetectable until it was too late. A spacecraft crossing its path wouldn't see a warning sign, no accretion disk, no glowing halo, or just sudden, catastrophic tidal forces. At close range, the gravitational gradient could shred a ship like taffy, warping its structure atom by atom. Even a near miss might slingshot a vessel off course with no hope of recovery, stranding it in the void. If these black holes drift plentifully through galactic arms, they'd turn the cosmos into a minefield, making long-distance travel a lethal gamble. But the danger might run deeper than navigation. Early-stage civilizations could face existential threats from black holes they never see coming. Picture a planet orbiting what appears to be a stable star, unaware that a primordial black hole hides in their solar system's outskirts. Over millennia, its gravitational nudges could destabilize asteroids, flinging them inward in catastrophic bombardments. Worse still, if the black hole's orbit decays, it might eventually plunge into the star itself, triggering violent shocks in the stellar core. Suddenly, a thriving civilization's sun could flare unpredictably or collapse prematurely, extinguishing life before it develops radio telescopes or spaceflight. The timing adds another grim layer. Primordial black holes aren't evenly distributed. They'd cluster in regions where density fluctuations were strongest in the early universe. If Earth sits in a relatively sparse bubble, we might have dodged these unseen bullets long enough to evolve, while civilizations in denser regions were snuffed out repeatedly. It's a chilling twist on the rare Earth hypothesis. Not that life-friendly planets are scarce, but that most are doomed by invisible gravitational time bombs. Yet the paradox cuts both ways. Some theorists argue that advanced civilizations might actually harness primordial black holes as power sources, tapping their Hawking radiation or using them as gravitational anchors for propulsion. If that's true, their absence could imply something worse, that every society reaching for the stars eventually unlocks these objects, only to fall victim to a fatal miscalculation. A single engineered black hole gone rogue could annihilate a civilization in hours, leaving behind no trace but a brief gamma-ray whisper, the sobering takeaway. Primordial black holes might be the universe's ultimate filter, not by design but by sheer cosmic indifference. While we search the skies for signals, the silence we perceive could be the echo of countless civilizations that never saw what hit them. And if we're wrong about how many of these gravitational ghosts drift among the stars, humanity's future among them might hinge on a single, harrowing question: are we alone because we're lucky or just next in line? Gravitational waves have revolutionized astronomy, giving us ears to hear the universe's most violent collisions. But what if some of these cosmic tremors aren't from dying stars at all, but from primordial black holes crashing together in the dark? When LIGO first detected gravitational waves in 2015, the signal came from two stellar mass black holes merging, a spectacular confirmation of Einstein's predictions. Yet hidden in the data might be whispers of something far older. Primordial black hole mergers would leave distinct fingerprints, offering physicists a chance to catch these elusive relics in the act. The key lies in the masses involved. Stellar black holes form from collapsing stars, so their weights follow certain rules, typically between 5 and 50 times the mass of our Sun. But primordial black holes, they could be almost anything. Imagine detecting a merger where one black hole weighs less than an asteroid, or a pair combining to form something far heavier than any star could produce. These outliers would stick out like sore thumbs in gravitational wave catalogs, defying conventional formation theories. Some models even predict mergers where the black holes have wildly different masses, say, one as light as the Moon and another rivaling a star. Such mismatched pairs would be nearly impossible to explain without invoking primordial origins. Then there's the frequency. If primordial black holes make up a significant fraction of dark matter, their mergers should produce a steady background hum of gravitational waves, a chorus of collisions too faint to pick out individually but detectable as statistical noise. Advanced LIGO and its successor, the Einstein telescope, might soon sift through this cosmic static, hunting for patterns that betray a hidden population of ancient black holes. The real jackpot would be catching one of these events at the edge of the observable universe, where the signal's redshift reveals an impossibly early merger date, proof the black holes existed before the first stars even ignited. But the smoking gun could come from the waves themselves. Primordial black holes likely formed without the messy accretion disks and stellar companions of their modern counterparts. When they collide, their gravitational waveforms should be cleaner, with fewer distortions from surrounding gas or magnetic fields. Some theories even suggest their mergers might ring space-time differently, producing higher frequency, chirps, or longer-lasting echoes, subtle quirks that would scream, "We're not from around here." Future detectors like LISA, sensitive to lower frequencies, could catch bigger primordial black holes merging in slow motion, their drawn-out spirals encoding clues about their birth. Critics argue we haven't seen conclusive evidence yet, but the search is just heating up. Every strange gravitational wave event, like the head-scratching merger dubbed GW 1924-26, where one object fell into the mysterious mass gap between neutron stars and black holes, fuels speculation. Others counter that primordial black holes would merge too rarely to explain LIGO current detection rates, unless they're clumped in dense, invisible clusters. Either way, each new observatory brings us closer to solving the puzzle. The implications stretch beyond astrophysics. Confirming primordial black hole mergers would give us a direct line to the universe's first second, letting us test theories of quantum gravity and inflation in ways particle colliders never could. These collisions might even reveal whether space-time has hidden dimensions or fractal structure at the smallest scales. Every chirp, every ripple could be a message carved in gravity itself, waiting for us to decipher its ancient code. And if we're listening closely enough, the cosmos might finally answer one of its oldest riddles, whether black holes were here before anything else. At the heart of a primordial black hole, buried beneath layers of crushing gravity, might lie one of the universe's most bizarre objects, a Planck star. Forget the infinite density of a singularity. quantum physics suggests something far stranger could lurk in these ancient cores. Picture matter compressed not into a dimensionless point, but to the smallest possible volume allowed by nature, the Planck length, 100 trillion times smaller than an atom. Here, the fabric of space-time rebels against further collapse, creating a dense, fiery remnant that defies everything we know about black hole interiors. This isn't just theoretical whimsy. Loop quantum gravity, a leading candidate for unifying quantum mechanics and relativity, predicts that collapsing matter doesn't vanish into oblivion. Instead, it rebounds at this unimaginably tiny scale, like a spring coiled to its limit. The result, a Planck star, a smoldering ember of primordial matter trapped inside the black hole's event horizon, radiating heat but forever hidden from our view. Unlike classical black holes, which trap everything behind an inescapable curtain, these quantum-corrected versions might have a beating heart at their center, pulsating with energy from the dawn of time. The implications ripple outward. If Planck stars exist within primordial black holes, their quantum pressure could dramatically alter how these objects behave. Hawking radiation, normally a slow leak, might spike unpredictably as the star's energy interacts with the event horizon. Collisions between two such black holes could produce gravitational wave signatures with bizarre echoes ripples that bounce off the internal Planck core before escaping into space. Even their evaporation could end not with a silent pop, but a final, brilliant flash as the trapped star is released, like a cork finally bursting from a bottle. Critics argue that detecting these effects borders on impossible. How do you study something forever hidden behind an event horizon? But here's where primordial black holes offer a unique window. The smallest ones, with event horizons no wider than a proton, might let quantum quirks peek through. As they evaporate via Hawking radiation, the Planck star's presence could subtly tweak the energy spectrum of emitted particles, leaving fingerprints in gamma-ray data. Some theorists even speculate that certain high-energy cosmic rays particles with energies that defy conventional explanations could be shrapnel from dying Planck stars, flung across the cosmos when their enclosing black holes finally dissipated. The most mind-bending possibility, Planck stars might not stay trapped forever. If a primordial black hole evaporates completely, the compressed remnant at its core could theoretically rebound outward, explosively releasing all that pent-up quantum energy. It's a cosmic resurrection, a black hole's death giving birth to a new, ultra-dense object that defies classification. Some models suggest these reborn Planck stars could briefly shine with the light of a supernova before cooling into strange, crystalline forms of matter unlike anything in the known universe. Whether or not Planck stars exist, their theoretical existence challenges our understanding of black holes as cosmic dead ends. Instead of tombstones, primordial black holes might be nested puzzles containing within them relics of physics operating at scales we can't yet probe. Every unexplained burst of radiation, every anomalous gravitational wave, could be a clue pointing toward these hidden stellar ghosts, and if we ever confirm their presence, it would mean the universe's oldest black holes aren't just empty pits of gravity, but safes locking away secrets from the very edge of reality. Some of the strangest mysteries in our solar system aren't found in distant nebulae or swirling galaxies. They're hiding in plain sight, tucked inside the familiar worlds orbiting our sun. Take Neptune's bizarrely warped orbit or the unexplained heat radiating from Jupiter's core. Conventional explanations fall short, but there's a radical possibility lurking in the shadows. What if planets are hiding primordial black holes within them or circling them unseen? This isn't just wild speculation, it's a theory born from glaring inconsistencies. Neptune's orbit wobbles in ways that defy predictions, as if something massive but invisible is tugging at it. The usual suspect, Planet 9, remains elusive after years of searching, but swap that hypothetical world for a primordial black hole of similar mass and suddenly the math clicks. A black hole with 10 times Earth's mass would exert the same gravitational pull as a rogue planet, but leave no trace of reflected sunlight. It would be the ultimate cosmic hide-and-seek champion, bending space just enough to perturb Neptune's path while remaining utterly undetectable to telescopes. Then there's Jupiter, pumping out more heat than models predict. Normally, this excess gets chalked up to leftover energy from its formation. But simulations show even that shouldn't account for the sheer amount radiating from its core unless there's an extra energy source. Enter a chilling possibility, a tiny primordial black hole, no wider than a hydrogen atom but as massive as a mountain, trapped deep within Jupiter's liquid metallic hydrogen ocean. As it slowly consumes matter, the black hole would release torrents of radiation, acting like a nuclear furnace at the planet's heart. It's a cosmic Russian nesting doll, a gas giant unknowingly harboring a relic from the universe's birth. The moon might be in on the secret too. Lunar seismometers left by Apollo astronauts recorded mysterious tremors dubbed moonquakes, some originating hundreds of kilometers below the surface. While most are blamed on tidal stresses, a handful defy explanation unless tiny black holes are zipping through the moon's interior, their gravity rippling the rock like stones dropped in water. Even Earth isn't immune. Some geophysicists speculate that certain deep mantle plumes, like the one feeding Hawaii's volcanoes, could be heat signatures from a micro-black hole lodged near the core, its gravitational friction cooking the surrounding rock over eons. Skeptics counter that such black holes would eventually devour their host planets, but physics offers a surprising reprieve. A black hole weighing less than a small asteroid would accrete matter so slowly, just a few kilograms per century, that it wouldn't noticeably affect a planet's lifespan. Over billions of years, its impact would be negligible compared to natural planetary cooling. Others argue these objects should have evaporated via Hawking radiation by now, but that hinges on their initial mass. A primordial black hole heavier than 1 billion metric tons could still be thriving today, its decay rate glacial compared to the age of the solar system. The real test, looking for subtle anomalies in planetary orbits or heat flows that no conventional model can explain. Missions like the upcoming Europa Clipper could inadvertently gather clues. Unexpected gravitational tugs during flybys might betray a hidden black hole's presence. Even household tech plays a role. Atomic clocks on GPS satellites occasionally glitch due to minuscule time distortions. While usually blamed on relativity, a drifting primordial black hole passing through Earth's neighborhood could produce similar ripples in spacetime, leaving fingerprints in precision timing data. If proven, this theory would rewrite our solar system's history. Rather than a tranquil family of planets, we'd live in a cosmic menagerie where some worlds are unwitting prisons for ancient gravitational monsters. Earth's stable orbit, Jupiter's furnace-like core, even the icy shells of distant moons, all might bear the invisible scars of collisions with black holes formed at the dawn of time. And if that's true, then every planet we study isn't just a world, but potentially the guardian of a secret older than the stars themselves. The universe's first microseconds were a seething ocean of quark-gluon plasma, a state so extreme that protons and neutrons hadn't even formed yet. In this primordial soup, particles moved with such energy that the fundamental forces we know today were still merged into one. It's within this bizarre environment that primordial black holes might have found their strangest breeding ground. Imagine chunks of this plasma cooling unevenly, creating pockets dense enough to collapse under their own gravity before ordinary matter could even take shape. These wouldn't be black holes as we understand them now, but something far stranger, knots of pure quantum chaos frozen in time. The quark-gluon plasma wasn't just hot, it was a roiling frontier where the rules of physics blurred. Under normal circumstances, quarks are forever bound together by gluons, never existing alone. But in those first moments, temperatures exceeded trillions of degrees, making the plasma a frenzied dance of free quarks and gluons. When certain regions of this plasma cooled slightly faster than their surroundings, the sudden pressure drop could have triggered gravitational instabilities. Picture syrup on a cold plate. The outer edges thicken first, creating ripples and clumps. Now scale that up to cosmic proportions, with clumps so massive they warp space-time itself into black holes long before the first atoms even twinkled into existence. These early black holes would have carried unique signatures. Unlike stellar black holes born from collapsing stars, quark-gluon black holes might have formed with exotic, hair, quantum traces of the plasma's original state clinging to their event horizons. Some theories suggest they could even have been temporary, blinking in and out of existence as the plasma's wild fluctuations stabilized. Others propose that quantum entanglement between the quarks in the plasma might have imprinted itself on the black holes, leaving them with properties no modern black hole could replicate. It's as if these objects were frozen snapshots of the universe's most chaotic adolescence, but the real shocker, these black holes might have shaped the plasma itself. Just as stirring cream into coffee creates whirlpools, primordial black holes plowing through the quark-gluon soup would have left turbulence in their wake. This could explain why matter isn't perfectly evenly distributed in the universe today. Those tiny gravitational ripples might have seeded the galaxies and voids we see billions of years later. Even more mind-bending, some models suggest that black holes formed during this phase could have absorbed and locked away asymmetries in the early universe, resolving mysteries like why there's more matter than antimatter. Detecting these relics would require rethinking our tools. Traditional methods like searching for gravitational lensing or Hawking radiation might miss quark-gluon black holes entirely if their quantum signatures differ from modern ones. Instead, physicists are hunting for imprints left in the cosmic microwave background, subtle temperature variations that could reveal where primordial black holes stirred the plasma like spoons in a pot. Others are simulating quark-gluon conditions in particle colliders, hoping to spot micro-black holes forming and evaporating in nanoseconds. While no smoking gun has emerged yet, each experiment brings us closer to glimpsing a universe where black holes weren't the end of matter's story, but its very first punctuation marks. The implications rewrite cosmic history. If primordial black holes truly emerged from quark-gluon plasma, they wouldn't just be oddities, they'd be active players in shaping the universe's structure. Their gravity could have acted like cosmic cookie cutters, carving out regions where matter later condensed into galaxies. Some might even have survived to today, hiding in dark matter halos with quark-era secrets encoded in their cores. It's a humbling thought. The black holes we strain to detect with billion-dollar telescopes might be the universe's original architects, their blueprints written in a language of quarks and gluons we're only beginning to decipher. Time crystals sound like something straight out of science fiction structures that repeat not in space like ordinary crystals, but through time itself, forever cycling without energy input. These bizarre quantum states were once thought impossible until researchers created them in labs using delicate atomic arrangements. Now, imagine that same phenomenon occurring naturally inside the universe's oldest gravitational traps. Some physicists speculate that certain primordial black holes could harbor time crystal structures in their cores, turning these cosmic relics into clocks older than stars. At the heart of this theory lies a quantum quirk. In a lab, time crystals form when particles get trapped in a never-ending loop, flipping between states like an unstoppable metronome. Translate that to a black hole's interior where gravity warps space-time to extremes, and you get a tantalizing possibility. Quantum fields near the event horizon might lock into similar rhythmic patterns. Unlike man-made time crystals, which require precise laser pulses to maintain, a black hole's crushing gravity could sustain these oscillations indefinitely, driven by the chaotic dance of virtual particles at its edge. Picture a celestial grandfather clock where the pendulum swings not with gears, but with the fundamental vibrations of space-time. what makes primordial black holes special candidates. Their formation in the universe's infancy means they've endured eons of quiet isolation, free from the disruptive forces that plague stellar black holes. No infalling matter, no violent mergers. This pristine environment could preserve delicate quantum behaviors that would otherwise get scrambled. If time crystal structures did emerge, they'd be frozen snapshots of quantum physics operating at energies we can't recreate, carrying imprints of the universe's first moments. Some models even suggest these time crystals could modulate Hawking radiation, causing the black hole to tick like a cosmic beacon, emitting pulses at predictable intervals across billions of years. The implications get stranger. If a black hole's interior becomes a time crystal, it might develop properties defying classical physics. Normally, anything crossing the event horizon is lost forever, but a time crystalline core could theoretically store information in its repeating patterns, like grooves on a vinyl record spinning at the edge of reality. This could offer a backdoor solution to the black hole information paradox, with data preserved not in two-dimensional holograms as standard theories suggest, but in rhythmic quantum fluctuations. Even more radical is the idea that these black holes might remember their formation conditions through their crystal structure, encoding the temperature and density of the early universe in their eternal cycles. Detecting such a black hole would require rethinking our approach. Instead of searching for gravitational waves or lensing effects, astronomers might need to hunt for anomalies in evaporating black hole signatures, peculiar bursts of radiation arriving in perfect intervals, or Hawking radiation spectra with unexpected periodic spikes. Experiments like quantum simulators could mimic these conditions, creating miniature black hole analogs to test whether time crystal behaviors emerge under extreme warping. Even unexplained pulsations in cosmic background radiation might hint at distant time crystal black holes ticking away in the void. Skeptics argue that maintaining quantum coherence in a black hole's chaotic environment seems impossible, but that's exactly why primordial specimens offer hope. Their simpler histories and potential lack of accretion disks might make them cosmic quiet zones where delicate quantum states survive. If proven, this theory would blur the line between quantum physics and relativity, revealing black holes not as destructive voids but as intricate timekeeping devices, each one a relic clock set in motion at the dawn of the universe, still ticking silently in the dark. One of the deepest puzzles in modern physics isn't about what black holes destroy, it's about what they might preserve. The black hole information paradox cuts to the heart of our understanding of reality. According to quantum mechanics, information can never truly vanish, yet black holes appear to erase it completely when matter crosses their event horizons. This contradiction has stumped physicists for decades, but primordial black holes born under radically different conditions than their stellar counterparts might hold the key to unraveling the mystery. The core of the paradox lies in black holes' terrifying simplicity. When a star collapses into a black hole, all the intricate details about that star, its composition, the arrangement of its atoms, even the family of cosmic events that birthed it seem to vanish behind an event horizon, leaving only three detectable properties: mass, spin, and charge. This no-hair theorem suggests black holes are cosmic bald spots, erasing complexity in favor of brute gravitational force. But quantum mechanics insists that information can't be destroyed. It might scramble, but it must persist. So where does it go? Primordial black holes offer a tantalizing solution. Unlike stellar black holes formed from chaotic stellar collapse, these ancient relics might have emerged through quantum processes in the early universe, carrying imprints of their birth conditions in ways we're only beginning to understand. Some theories propose their event horizons could behave like holographic plates, encoding infalling information in two-dimensional quantum pixels on their surfaces, a concept known as the holographic principle. Because primordial black holes lack the messy accretion disks and violent formation histories of their modern cousins, their holograms might be far clearer to decode, like comparing a pristine fossil to a weathered one. Another radical idea hinges on quantum entanglement, the eerie connection between particles that links their fates across vast distances. If primordial black holes formed when the universe was still a seething quantum soup, their interiors might preserve entanglement networks from that era. Instead of information being lost, it could be transferred into these quantum threads, woven into the fabric of space-time itself. Picture a library where books aren't burned but translated into a language woven into the walls, a language only quantum gravity can read. The real test comes when these black holes evaporate. Hawking radiation, the slow leak of energy that causes small black holes to fade away, should theoretically carry no information about what fell in. But if primordial black holes encode data differently, perhaps through Planck-scale vibrations or time crystal structures, their evaporation could release subtle information-laden signatures. Astronomers might one day detect anomalies in gamma-ray bursts from evaporating black holes, patterns that resemble cosmic barcodes revealing what these objects consumed billions of years ago. Critics argue this sidesteps the paradox rather than solving it, but the stakes couldn't be higher. If primordial black holes preserve information differently, they'd force us to rewrite the rules of quantum mechanics, relativity, or both. Every unexplained ripple in gravitational wave data or oddball gamma-ray signal brings us closer to an answer, not just about black holes, but about whether the universe itself keeps perfect records. The irony is delicious. The darkest objects in existence might be the very things that illuminate how reality stores its secrets. Deep beneath the Antarctic ice, sensors buried in a cubic kilometer of pristine frozen water occasionally light up with eerie blue flashes, the telltale sign of high-energy neutrinos piercing Earth from deep space. These ghostly particles, arriving from cosmic catastrophes billions of light-years away, carry whispers of the universe's most violent events. But here's the puzzle. Not all neutrinos fit neatly into known sources like supernova or black hole mergers. Some blaze with energies that defy explanation, as if something far stranger is hurling them across the cosmos. That's where primordial black holes enter the scene, not as silent gravitational traps, but as potential neutrino factories, flinging these ghost particles into space in ways we're only beginning to unravel. Picture a primordial black hole drifting through a cloud of interstellar gas. Unlike its stellar mass cousins, which tear matter apart in blazing accretion disks, this ancient relic might feed more subtly. As atoms spiral inward, they don't just heat up, they collide with such violence that protons and neutrons shatter into quark-gluon shrapnel. In these chaotic conditions, particles called pions form and decay almost instantly, producing neutrinos with energies millions of times greater than those from our Sun. Now imagine this process happening on a cosmic scale, with countless primordial black holes scattered through galactic halos, each acting like a stealthy particle accelerator. The result, a diffuse rain of high-energy neutrinos, their origins untraceable to any visible source, washing over detectors like ice cube in inexplicable bursts. But the neutrino connection gets stranger. Some theories suggest these black holes might not just produce neutrinos, they could transform them. Quantum gravity effects near a microscopic event horizon could twist neutrino oscillations in ways standard physics can't explain, morphing them between flavors electron, muon, tau at bizarre rates. Detectors might spot clusters of neutrinos arriving with impossible energy distributions or flavor ratios that don't match known astrophysical models. These anomalies could be fingerprints of primordial black holes warping particles in their gravitational jaws before flinging them outward. Then there's the annihilation angle. If dark matter consists of weakly interacting massive particles WIMP, colliding near a primordial black hole's intense gravity well, their mutual destruction could spawn neutrino jets alongside gamma rays. This 2-for-1 signature high-energy neutrinos paired with specific photon emissions might reveal black holes too small to detect otherwise. Astronomers are already cross-referencing unexplained neutrino events with gamma-ray telescope data, hunting for these coincidences that could betray a hidden population of gravitational traps. The most tantalizing clues come from ghost particle events with no visible counterpart. In 2022, IceCube detected a neutrino with a staggering 4.5 petelectronvolts of energy, the most powerful ever recorded, yet telescopes saw nothing at its origin point. Traditional explanations like blazars or gamma-ray bursts came up empty, but a primordial black hole passing through a dense molecular cloud could generate such a neutrino without the usual electromagnetic fanfare, its gravity accelerating particles to extreme energies invisibly. If just a fraction of these orphan neutrinos trace back to ancient black holes, it would mean we've been surrounded by cosmic ghost makers all along. Their neutrino whispers the only sign of their existence. Critics point out that neutrino astronomy is still in its infancy. Many sources remain unconfirmed, but that's precisely what makes this theory so compelling. As detectors grow more sensitive, we might spot patterns aligning with primordial black hole distributions rather than galaxies, or neutrinos arriving in time with microlensing events. The next generation of neutrino observatories, like the planned Pacific Ocean Array, could finally provide the resolution needed to map these particles back to their stealthy accelerators. Every unexplained high-energy neutrino isn't just a mystery. It's a potential breadcrumb leading us to the universe's oldest gravitational ghosts. Cosmic rays have puzzled scientists for over a century. Charged particles screaming through space at nearly light speed, some carrying energies 1,000,000 times greater than anything our most powerful particle colliders can produce. We've traced many to violent sources like supernova remnants and active galactic nuclei, but the most energetic ones remain shrouded in mystery. Their origins demand something far more extreme than ordinary astrophysical processes, something capable of launching protons and atomic nuclei across the cosmos like cosmic bullets. Enter primordial black holes, nature's ultimate particle accelerators, lurking unseen while hurling matter to unimaginable velocities. The secret lies in their unmatched gravitational efficiency. Picture a proton drifting near a microscopic black hole weighing as much as a mountain. As it crosses the event horizon, a boundary narrower than an atom, the gravitational gradient becomes so steep that space itself acts like a slingshot. Unlike the messy turbulence around stellar black holes, where particles collide and lose energy in accretion disks, a primordial black hole's clean gravitational field can accelerate particles with terrifying precision. It's the difference between a haphazard explosion and a rifle shot. Both release energy, but one channels it with deadly focus. Calculations show particles whipped around these tiny gravitational vortices could reach energies exceeding 10 to the 20th electron volts, making the Large Hadron Collider look like a toy in comparison. These black holes wouldn't just accelerate particles, they'd stamp them with unique signatures. When a proton gets torn apart near the event horizon, its quark constituents might recombine into exotic particles like strangelets or magnetic monopoles before being ejected. Telescopes have occasionally spotted cosmic rays with bizarre composition, ratios, atomic nuclei sporting unusual combinations of protons and neutrons, or even traces of antimatter. These outliers fit uncomfortably with conventional acceleration theories, but they're exactly what you'd expect from matter being shredded and reassembled in the quantum chaos near a microscopic black hole's maw. The distribution of ultra-high-energy cosmic rays adds another clue. These particles arrive from all directions with no obvious source, as if the entire universe were peppered with invisible accelerators. Remarkably, their arrival patterns loosely align with gravitational lensing maps of dark matter halos, regions where primordial black holes would naturally cluster if they're indeed the missing mass of the cosmos. It's a subtle hint, but one that grows harder to ignore as detectors like the Pierre Auger Observatory accumulate more data. Some events even show particle showers with anomalous zenith angles, suggesting they encountered intense gravitational fields en route to Earth, fields far stronger than anything a passing star or gas cloud could provide. But the real smoking gun might come from paired emissions. When a particle gets accelerated near a black hole, it often radiates gamma rays or neutrinos as a byproduct. Several unexplained cosmic ray events coincide with faint gamma ray bursts too short-lived to originate from collapsing stars or merging neutron stars. If these flashes trace back to regions devoid of visible matter, they could be the farewell fireworks of particles launched by primordial black holes' gravitational railguns firing their payloads across the galaxy. Critics argue that we should have detected more gamma-ray counterparts if this process were common, but that assumes all black holes are actively feeding. A dormant primordial black hole drifting through near-perfect vacuum would accelerate the rare particles it encounters almost silently, like a hidden whirlpool in a nearly still pond. Only when one passes through a molecular cloud or the outskirts of a star's atmosphere would the particle flux spike enough to produce noticeable secondary emissions. This variability could explain why some ultra-high-energy cosmic rays arrive with electromagnetic partners, while others seem to materialize from empty space. The implications stretch beyond astrophysics. If primordial black holes are indeed cosmic ray factories, their output could serve as a natural laboratory for physics we can't recreate on Earth. Particles accelerated to Planck-scale energies might briefly probe hidden dimensions or reveal quantum gravity effects before disintegrating in our atmosphere. Some theorists even speculate that certain rare particle showers like the infamous Oh My God particle detected in 1991 could carry imprints of spacetime's granular structure etched into them during near-light-speed encounters with black hole event horizons. Every unexplained cosmic ray becomes a potential messenger from the quantum frontier, carrying secrets from the universe's most efficient accelerators, ones that have been operating in stealth mode since the dawn of time. Dark energy and primordial black holes seem like cosmic opposites, one an invisible force stretching space apart, the other a gravitational pit pulling everything inward. But what if these two mysteries of the universe are locked in a hidden dance, shaping the fate of the cosmos in ways we've barely begun to imagine? The PBH dark energy interaction hypothesis turns conventional cosmology on its head by suggesting these ancient black holes might be cosmic counterweights, subtly resisting the universe's accelerating expansion. At first glance, the idea seems absurd. Dark energy operates on the grandest scales, uniformly accelerating galaxies apart, while primordial black holes are local gravitational anomalies. Yet consider this: if enough of these black holes formed during the universe's infancy, their collective gravity could create subtle drag against dark energy's push. Picture a vast rubber sheet representing space-time. Dark energy stretches it outward, while countless tiny black holes act like minuscule anchors, creating dimples that slightly slow the stretching in their vicinity. Over billions of years, this tug-of-war might leave faint fingerprints in how fast certain regions of the universe expand compared to others. The math gets even wilder when you account for Hawking radiation. As primordial black holes slowly evaporate, they release energy back into space. In regions densely populated with these objects, this steady energy injection could counteract dark energy's thinning effect, like adding drops of water to an evaporating puddle. Some models suggest this process might explain why measurements of the universe's expansion rate, the Hubble constant, don't always agree. Local variations in primordial black hole densities could create cosmic neighborhoods where space expands slightly slower, throwing off our cosmic yardsticks. Then there's the space-time curvature angle. Dark energy is thought to arise from the vacuum of space itself, but near a black hole's event horizon, quantum effects twist the vacuum into knots. If primordial black holes warp the quantum foam differently than modern black holes, say, Due to their unique formation conditions, they might locally alter how dark energy behaves. It's like stirring honey into tea. The viscosity changes where the spoon disturbs it. On cosmological scales, these microscopic disturbances could add up, potentially explaining why dark energy's strength appears curiously fine-tuned for life to exist. Critics counter that the numbers don't add up. There likely aren't enough primordial black holes to meaningfully resist dark energy's dominance. But here's where the hypothesis takes an even stranger turn. If some fraction of these black holes became cosmologically stuck during evaporation, perhaps due to quantum gravity effects, they could persist as gravitational fossils, their accumulated influence growing over time. Others speculate that certain dark energy models incorporating extra dimensions might allow black holes to leak gravitational influence into hidden realms, effectively amplifying their cosmic impact. The most tantalizing evidence might come from deep space anomalies. Astronomers have spotted distant galaxy clusters moving slightly faster than dark energy models predict, as if tugged by unseen gravitational sources. While usually attributed to the cosmic web's large-scale structure, an alternative explanation whispers of primordial black hole halos surrounding these clusters, their combined mass subtly bending the expansion. Future telescopes like the Roman Space Telescope could map these peculiar velocities in unprecedented detail, searching for patterns that align with predicted black hole distributions rather than visible matter. Whether or not this hypothesis holds, it forces us to confront a profound possibility. The universe's expansion might not be a simple battle between gravity and dark energy, but a complex symphony where ancient relics play unexpected roles. Every unexplained deviation in the Hubble constant, every odd galaxy motion, could be a clue that the cosmos remembers its violent birth through black holes that refuse to fade quietly into the dark. One of the most mind-bending ideas in modern physics suggests that black holes might not be three-dimensional objects at all, but cosmic holograms with all their information painted across two-dimensional surfaces. This holographic principle, first proposed to solve the black hole information paradox, takes on new dimensions when applied to primordial black holes. Unlike their stellar-born cousins, which form through messy stellar collapses, these ancient relics might preserve quantum data in ways that make them ideal testing grounds for holographic theories, if we could just peek behind the curtain. At first glance, the concept seems absurd. How could all the complexity of a black hole's interior, with its unfathomable gravitational depths and quantum chaos, be perfectly represented on a flat surface? The answer lies in the strange behavior of quantum information. Just as a hologram encodes a 3D image in a 2D film using light interference patterns, a black hole's event horizon could theoretically store quantum bits in Planck-scale pixels, each carrying data about everything that ever fell in. For stellar black holes, this hologram gets scrambled by violent formation processes and chaotic accretion. But primordial black holes, born in the quiet quantum fluctuations of the early universe, might carry cleaner, more decipherable holographic imprints like fossils frozen in perfect amber. The implications grow wilder when you consider scale. A primordial black hole with the mass of a mountain would have an event horizon smaller than a proton, yet the holographic principle suggests this microscopic surface could hold information equivalent to an entire universe's worth of quantum data. Imagine squeezing the Library of Congress into a single snowflake, then realizing every letter remains perfectly readable if you know how to look. This extreme data compression might explain why these black holes don't evaporate instantly. Their quantum hard drives are so efficient that Hawking radiation leaks out information at an agonizingly slow pace stretched across billions of years. Critics argue we'll never test this directly. How do you scan a surface that exists behind an inescapable gravitational barrier? But primordial black holes offer a backdoor. Their smaller size means quantum effects near their event horizons are magnified, potentially leaving faint signatures in their evaporation patterns. As they emit Hawking radiation, the precise spectrum of particles could carry echoes of the holographic code, like static from a corrupted radio transmission. Some models even suggest that certain statistical anomalies in gamma-ray bursts, tiny deviations from predicted emission curves, might reveal whether information is leaking from a 2D surface rather than a 3D volume. The deepest mystery lies in what these holograms might encode. If primordial black holes formed during cosmic inflation, their surfaces could preserve snapshots of the universe's first quantum fluctuations data that normally vanished as space expanded. They might even hold traces of pre-inflation physics, a regime completely inaccessible by any other means. It's as if the universe, anticipating our curiosity, left encrypted thumb drives scattered across space-time. And if we ever learn to read them, we might discover that the darkest objects in existence are also the universe's most perfect mirrors, reflecting creation's first moments in Planck-scale pixels too small to see but too precise to ignore. What if the Big Bang wasn't the beginning, just a violent transition in an endless cycle of cosmic rebirth? Some physicists speculate that primordial black holes could be the last survivors of a previous universe, ancient relics squeezed through the Big Bang's fiery gates to haunt our own. This radical idea, known as conformal cyclic cosmology, suggests that time doesn't have a start or end point, but loops eternally like a Möbius strip. In this model, when one universe ends in a sea of evaporating black holes, their final moments seed the next cosmic dawn, and primordial black holes might be the only structures sturdy enough to bridge the gap. Think of space-time as a sheet of paper crumpled into a ball during the Big Crunch, the hypothetical collapse of a previous universe. Most structures would be shredded beyond recognition, but black holes, with their indestructible event horizons, might persist like wrinkles in the paper that survive being smoothed out. As the next universe inflates from the singularity, these gravitational scars could carry forward, their imprints warping the newborn cosmos in ways we're only beginning to decipher. It's as if the universe has a genetic code, and primordial black holes are the epigenetic markers passed between generations. The math behind this isn't pure fantasy. Under conformal symmetry, a principle where physics remains unchanged even as scales stretch or shrink, black holes could theoretically preserve their essential properties across universal resets. Their event horizons would act like cosmic sieves, filtering out the chaotic details of their parent universe while retaining topological memory. Some models suggest these pre-Big Bang black holes might even carry distinct spin signatures or quantum entanglement patterns that betray their extraterrestrial origins. Imagine detecting a primordial black hole whose rotation axis aligns with no known structure in our universe, a silent arrow pointing back to a reality that existed before time as we know it began. Critics argue this veers into untestable metaphysics, but observational clues might exist. If certain primordial black holes cluster in ways that defy our universe's large-scale structure, or if their evaporation spectra show particle ratios impossible under standard physics, they could be cosmic immigrants bearing foreign physics. Even more tantalizing, some versions of string theory predict that colliding brains' higher dimensional membranes could spawn black holes during cyclical universe collisions. These objects would contain twisted strands of extra-dimensional space in their cores, potentially leaking gravity into hidden dimensions in ways we could detect through subtle gravitational anomalies. The implications rewrite not just cosmology but philosophy. If primordial black holes are indeed time travelers from a pre-Big Bang era, studying them becomes akin to archaeology at the scale of reality itself. Their event horizons might hide layers of information like tree rings, each stratum encoding a different cosmic epoch. Some theorists even speculate that advanced civilizations in previous universes could have intentionally crafted black holes as time capsules, knowing they'd outlast the end of time. It's a dizzying thought, The darkest objects in existence might not just be relics, but messages, bottled notes floating in the ocean between cosmic shores. Black holes are cosmic one-way streets, or so we thought. Hidden in the equations of general relativity lies a bizarre possibility. These gravitational traps might have cosmic opposites called white holes, theoretical regions where matter and energy erupt outward instead of vanishing forever. Now imagine if some primordial black holes, after billions of years of silence, could flip this cosmic switch, transforming from devourers of light into radiant fountains of creation. This isn't science fiction, it's a serious proposal that could rewrite the life cycles of the universe's oldest black holes. The math behind this transformation is as elegant as it is mind-bending. In Einstein's theory, a black hole singularity, the point of infinite density at its core, isn't just a dead end. Under certain quantum conditions, it could theoretically tunnel through space-time to become a white hole singularity, like a wormhole turning itself inside out. For stellar black holes, this process would take longer than the current age of the universe, but primordial black holes, especially the tiniest ones, might have just had enough time. Picture a black hole with the mass of an asteroid, formed in the universe's first second. After slowly leaking Hawking radiation for billions of years, its final moments could trigger a quantum rebound, its collapsing core bouncing back as a white hole in a spectacular reversal of entropy. The aftermath would be unlike anything in known astrophysics. Instead of fading quietly, the reborn white hole would erupt with the energy of its accumulated Hawking radiation, potentially outshining entire galaxies for brief, dazzling instants. Some models suggest these explosions could mimic fast radio bursts or certain types of gamma-ray flashes, releasing energy in precise, quantized packets that betray their quantum origins. Even stranger, the ejected material wouldn't just be random particles, it might include matter that fell into the black hole eons ago, reprocessed by the white hole's quantum firewall into exotic forms we've never observed. Critics argue that white holes violate thermodynamics by seemingly creating energy from nothing, but the devil's in the quantum details. The transition wouldn't be a true violation. It would simply repackage the black hole's stored gravitational energy into explosive output, like a coiled spring finally releasing its tension. Observations might already hold clues. Astronomers have detected ultra-high-energy cosmic rays with no clear source, along with fleeting, ghost flashes in deep field surveys that vanish before follow-up observations. These could be the fingerprints of primordial white holes popping into existence, their brief luminous lives ending as swiftly as they began. The implications ripple across cosmology. If even a fraction of primordial black holes undergo this transformation, they could be seeding the modern universe with recycled matter from the cosmic dawn particles that haven't existed freely since the first seconds after the Big Bang. Some theorists speculate these white hole eruptions might even trigger star formation in nearby gas clouds, acting as cosmic wake-up calls for dormant regions of space. Others propose they could solve the mystery of certain antimatter signatures in our galaxy, with white holes spewing equal parts matter and antimatter as they quantum correct themselves out of existence. The hunt for these cosmic phoenixes is pushing detectors to their limits. Next-generation gravitational wave observatories might catch the telltale pop of space-time recoiling during a black-to-white transition, while gamma-ray satellites could spot the unique spectral lines of quantum reprocessed matter. There's even a provocative idea that dark matter particles could be white hole ash, lingering remnants of these explosions too subtle to detect directly. Every unexplained high-energy event in the cosmos becomes a potential candidate, a flash in the dark that might not be a star's death, but something far older waking from its gravitational slumber. Perhaps the most profound revelation isn't about physics, but time itself. If black holes can become white holes, then the arrow of entropy isn't just a one-way street, it's a loop where even the universe's darkest corners hold the potential for rebirth. These ancient objects wouldn't just be relics of the past, but time bombs of cosmic renewal, waiting to remind us that in the quantum wilds of space-time, nothing, not even a black hole's hunger, lasts forever. One of the greatest unsolved mysteries of cosmology isn't about what's present in the universe, it's about what's missing. For every billion particles of matter created in the Big Bang, there should have been an equal number of antimatter counterparts. Yet today, we live in a cosmos dominated by matter, with antimatter virtually non-existent. This baryon asymmetry problem has stumped physicists for decades, but primordial black holes might hold the key to this cosmic imbalance, not by creating matter, but by being the universe's most ruthless antimatter filters. Picture the seething chaos of the early universe, where particle-antiparticle pairs constantly formed and annihilated in a frenzied dance. Under normal circumstances, this process should have left perfect balance, equal parts matter and antimatter cancelling out into pure energy. Yet somehow an asymmetry slipped through. Here's where primordial black holes enter the scene. Their extreme gravity could have acted like a cosmic sieve, preferentially capturing antimatter due to subtle differences in how these particles interact with curved space-time. Some theories suggest that antimatter's slightly stronger gravitational response, a phenomenon called gravitational baryogenesis, would have made them more likely to fall into these microscopic gravitational traps, effectively removing them from the cosmic ledger while leaving ordinary matter to dominate. The mechanism gets even more intriguing when quantum effects come into play. Near a black hole's event horizon, virtual particle pairs constantly blink in and out of existence. Normally, they annihilate instantly, but in the intense gravitational field, one particle might escape while its antiparticle counterpart gets trapped inside. If primordial black holes had even a 1% preference for absorbing antimatter over matter across the entire observable universe, that tiny bias could explain today's overwhelming matter dominance. It's like a casino where the house always wins over enough rolls of the dice. Even a slight statistical edge reshapes the entire game. But there's a wilder possibility that primordial black holes didn't just filter antimatter but actively transformed it. Certain grand unified theories predict that black holes can violate baryon number conservation, effectively reprocessing infalling particles. Imagine an antiproton falling into a microscopic black hole only to emerge through quantum tunneling effects as three quarks. This violation of standard particle physics would leave the universe with a permanent matter surplus, like a cosmic alchemist turning lead into gold at the event horizon's edge. Some calculations suggest this process could have been particularly efficient in the high-energy environment of the early universe, where primordial black holes acted as matter factories on a cosmological scale. The fingerprints of this process might still be detectable today. If primordial black holes preferentially consumed antimatter, regions with higher black hole densities in the early universe should show stronger matter-antimatter disparities. This could imprint specific patterns on the cosmic microwave background, subtle temperature variations that next-generation telescopes might soon resolve. Even more tantalizing are predictions that surviving primordial black holes could still occasionally leak baryon-violating radiation, producing exotic particles that our detectors would flag as impossible under standard physics. Critics argue that the numbers don't quite add up. The required antimatter absorption rates would demand more primordial black holes than most models allow. But this might just mean we're missing part of the picture. If black holes formed during phase transitions in the early universe moments when fundamental forces separated, they could have temporarily altered the laws of physics in their vicinity, creating localized pockets where matter gained irreversible advantage. It's a cosmic-scale version of freezing saltwater. As the ice forms, the remaining liquid becomes saltier by exclusion. In this case, primordial black holes were the ice and matter the concentrated brine. The implications reach beyond particle physics. If these ancient gravitational traps truly tipped the matter-antimatter scales, they didn't just shape the universe's composition, they made life itself possible. No asymmetry means no atoms, no stars, no planets, just an eternal sea of annihilating particles. Every galaxy, every star, every molecule in our bodies might owe its existence to primordial black holes' selective appetite, a quantum discrimination written in gravity that allowed something rather than nothing to endure. And if we ever confirm their role, it would mean the darkest objects in existence are also the reason there's light at all. Quantum entanglement, the bizarre phenomenon where particles remain mysteriously linked across vast distances, defies everything we know about classical physics. Now imagine scaling that weirdness up to cosmic proportions, where entire black holes could share this invisible connection. Primordial black holes, born in the quantum frenzy of the early universe, might be the ultimate entangled objects, their fates intertwined with other black holes or quantum systems in ways that rewrite the rules of space and time. The roots of this idea lie in the conditions of the Big Bang itself. When the universe was smaller than an atom, every particle and force existed in a quantum soup where entanglement wasn't just common, it was unavoidable. As inflation stretched space, these connections should have snapped like overextended rubber bands, but black holes, with their event horizons acting as quantum firewalls, could have preserved these links. Picture two primordial black holes forming from the same quantum fluctuation, their birth forever linking them like cosmic twins. Even if they now drift billions of light years apart, their spins, evaporation rates, or even the particles they emit might still move in perfect, instantaneous correlation, a phenomenon Einstein famously dismissed as spooky action at a distance, but which quantum mechanics insists is real. This isn't just theoretical hand-waving. In 2016, physicists proposed the ER=EPR conjecture, suggesting that entanglement EPR might be physically manifested as microscopic wormholes stitching black holes together through space-time's fabric. For primordial black holes, this could mean their event horizons are secretly connected by a network of Planck-scale tunnels, too tiny to traverse but robust enough to transmit quantum information. The implications are staggering. If two entangled black holes evaporate via Hawking radiation, the emitted particles might carry coordinated quantum states, creating a galactic-scale encryption key or a natural quantum communication network older than stars. The most tantalizing evidence could come from gravitational wave detectors. When two black holes merge, their final spin and ring-down vibrations should follow predictable patterns. But if one of those black holes was entangled with a distant third partner, subtle anomalies might appear, like a gravitational wave chirp with an unexpected echo or a spin axis that tilts suspiciously toward a specific patch of sky. Future observatories like LISA or the Einstein telescope could hunt for these statistical quirks, comparing merger events across the cosmos for correlated behaviors that betray hidden quantum handshakes. Critics argue that decoherence, the tendency of quantum systems to lose coherence through environmental interactions, should have severed these links over billions of years. But primordial black holes offer a loophole. Isolated in the cosmic void with no matter to disrupt their quantum states, these relics might have avoided the usual decoherence triggers. Their event horizons could act like quantum refrigerators, preserving entanglement at temperatures near absolute zero. Some models even suggest their Hawking radiation isn't random noise, but a slow decoding of quantum information shared across space-time, like a cosmic Morse code broadcasted by particles that remember their partners. The wildest possibility, primordial black holes might not just be entangled with each other, they could link to the universe's fundamental quantum fields. Imagine a black hole vibrating in sync with the Higgs field, its evaporation rate subtly modulating as the field's value changes elsewhere. Or consider the vacuum energy. If entangled black holes influence its fluctuations, they might create localized dark energy variations that sculpt the large-scale structure of the cosmos. It's a dizzying thought that the universe's darkest objects could be pulling invisible quantum strings, orchestrating reality from behind the curtain of event horizons. If proven, this connection would force us to rethink black holes not as endpoints, but as nodes in a vast quantum network, one woven at the universe's birth and still humming with hidden connections. Every gravitational wave, every unexplained particle emission, could be a clue that we're not just observing black holes, but glimpsing the threads stitching the cosmos together at its most fundamental level. And if we ever learn to read those threads, we might discover that the universe isn't just expanding, it's still entangled with itself, whispering secrets through black holes older than time. Wormholes have long been the stuff of science fiction cosmic tunnels connecting distant parts of the universe, or even different universes entirely. But buried in Einstein's equations is a tantalizing possibility. These spacetime shortcuts might not just be fantasy. Primordial black holes, with their exotic origins and quantum quirks, could be the universe's natural wormhole engineers, creating or stabilizing these passageways in ways modern black holes never could. The secret lies in the extreme conditions of the early universe. When space was a seething quantum foam, microscopic black holes might have formed with peculiar topological structures, not just as singularities, but as bridges between distant points in spacetime. Unlike the unstable wormholes predicted in general relativity, which require mythical, exotic matter to stay open, these primordial versions could have been forged with built-in stability. Picture a soap bubble stretched between two rings. The surface tension keeps it intact. In the same way, quantum effects in the infant cosmos might have twisted spacetime into self-reinforcing wormholes, with primordial black holes acting as their gravitational anchors. What makes these ancient black holes special is their potential connection to quantum gravity. As the universe cooled after the Big Bang, phase transitions in the fabric of reality could have left behind defects like cracks in ice where spacetime folded back on itself. Primordial black holes forming near these defects might have crystallized these folds into permanent structures. Some theories suggest their event horizons could disguise the wormhole's throat, hiding the tunnel behind an ordinary-looking gravitational trap. From the outside, it would resemble any other black hole, but instead of a one-way trip to oblivion, crossing the threshold could send you hurtling across the cosmos or to another time entirely. The real magic happens when you consider Hawking radiation in this context. As primordial black holes evaporate, their shrinking event horizons might expose the underlying wormhole structure, like receding floodwaters revealing a hidden canyon. Calculations show that certain quantum corrections could prevent the wormhole from pinching shut, effectively turning an aging black hole into a traversable gateway. It's as if the universe left emergency exits in its earliest moments, ones that only become accessible after billions of years of patient waiting. Observational clues might already exist. Certain gamma-ray bursts exhibit bizarre energy signatures that don't match known astrophysical processes. These could be the death throes of primordial black holes undergoing wormhole transitions, their final bursts of Hawking radiation tinted by exotic particles skimming the edge of a spacetime tunnel. Even more intriguing are cold spots in the cosmic microwave background, regions slightly cooler than their surroundings. Some theorists propose these could be imprints of primordial wormholes, their gravitational lensing subtly distorting the afterglow of the Big Bang. Critics argue that stabilizing wormholes would require physics far beyond our current understanding, but that's exactly why primordial black holes offer hope. Their formation during the quantum gravity epoch means they might operate under rules we're only beginning to glimpse. If even a fraction survived with intact wormholes, they'd rewrite not just our maps of the cosmos, but our understanding of causality itself. Imagine a civilization stumbling upon one of these relics suddenly. The universe's vastness becomes negotiable, its timelines malleable. The catch: these might be one-shot wonders, collapsing after a single use like cosmic toll booths demanding payment in entropy. The implications spiral outward. Wormhole-equipped primordial black holes could explain otherwise impossible cosmic connections, galaxies with eerily similar structures across billions of light-years, or particles that seem to share history despite never interacting. They might even offer a backdoor solution to the Fermi Paradox. Advanced civilizations didn't vanish, they simply bypassed our observational horizon through unseen shortcuts. Every unexplained gravitational anomaly or oddly correlated event in deep space becomes a potential signpost, hinting at a hidden network of tunnels woven into the fabric of reality by black holes older than time. Gamma-ray bursts are the universe's most violent explosions, blazing jets of energy so intense they outshine entire galaxies for a few fleeting seconds. While most are linked to collapsing stars or neutron star collisions, a stubborn fraction defy explanation, flashing with energies or durations that don't fit known astrophysical recipes. Hidden in these outliers might be clues to one of cosmology's most elusive mysteries: the fingerprints of primordial black holes acting out their final, spectacular acts. Take the case of short gamma-ray bursts, those lasting less than 2 seconds. Conventional wisdom ties them to mergers of dense stellar remnants, but some exhibit bizarre features. A handful arrive with energy spectra that spike in unexpected places, like a piano playing notes that don't belong to any known scale. Others flicker with quasi-periodic pulses, as if something is modulating the explosion with precise, rhythmic timing. These anomalies align eerily well with theoretical models of primordial black hole encounters. Imagine one of these ancient objects, weighing as much as a mountain but no wider than an atom, slamming into a neutron star. The collision wouldn't just release gravitational energy, it would twist the neutron star's immensely powerful magnetic fields like rubber bands, snapping them back to launch relativistic jets of gamma rays. The resulting burst would be shorter and sharper than typical mergers, with spectral fingerprints betraying the black hole's unique gravitational signature. Even stranger are the ultra-long gamma-ray bursts lasting minutes to hours. While usually attributed to the collapse of massive stars, a few lack the accompanying supernova expected from such cataclysms. Here's where primordial black hole evaporation enters the picture. According to Hawking's calculations, the smallest black holes should end their lives in a runaway explosion of radiation. As they shrink, their temperatures skyrocket, culminating in a final burst where the entirety of their mass converts to energy in milliseconds. But if that black hole is spinning, and primordial ones likely formed with extreme rotation, the energy release could stretch into a longer, modulated fireworks show. The spin would distort the emission, creating fluctuating brightness and spectral tilts unlike anything produced by stellar processes. Some astronomers argue that certain bursts, like the perplexing GB 060614, match this profile too closely to dismiss. Then there's the spatial distribution puzzle. Gamma-ray bursts should trace the universe's star-forming regions, where massive stars live and die violently. Yet deep sky surveys reveal a subset appearing in cosmic voids, regions nearly devoid of galaxies, let alone the massive stars needed to trigger conventional bursts. If primordial black holes populate these empty spaces as dark matter candidates, their rare collisions or evaporation events would naturally explain these field bursts with no stellar progenitors. It's like finding campfires in the middle of an ocean. The only plausible explanation is something drifting unseen beneath the surface. The most tantalizing evidence comes from multi-messenger observations. In 2019, a gamma-ray burst coincided with a high-energy neutrino, a ghostly particle that rarely interacts with matter. While neutrinos can be produced in stellar explosions, the energy of this particular particle far exceeded typical supernova outputs. A primordial black hole plowing through a dense molecular cloud, however, could accelerate particles to such extremes that neutrino production becomes inevitable. Later that same year, another burst paired with an unusual gravitational wave signal, a chirp too high-pitched to match merging stellar black holes. The timing raised eyebrows. Was this a chance alignment or the first hint of a primordial black hole encountering a compact object? Skeptics rightly point out gaps in the theory. If primordial black holes trigger gamma-ray bursts, why don't we see more of them? The answer might lie in the specifics of their formation. Only a narrow mass-range black holes weighing between 1 billion tons and a small asteroid would evaporate or collide within the current age of the universe, making their bursts rare but detectable. Others counter that we lack detailed models of how exactly a microscopic black hole would interact with neutron star matter or interstellar gas, but that's where next-generation telescopes come in. Upgraded instruments like the planned COSY gamma-ray satellite will analyze burst polarizations and spectral lines with unprecedented precision, hunting for the telltale signatures of quantum gravity effects or exotic particle production that would betray a primordial black hole's involvement. What makes this theory so compelling isn't just its explanatory power, it's the sheer audacity of the implications. If even a fraction of unexplained gamma-ray bursts trace back to primordial black holes, it means we've been overlooking an entire class of cosmic catastrophes. These wouldn't just be random collisions or dying stars, but the final moments of relics older than atoms themselves, detonating in ways that illuminate the quantum structure of spacetime. Every anomalous burst becomes a potential Rosetta Stone, waiting to decode the hidden language of the universe's earliest gravitational whispers. And if we're right, the night sky's most brilliant flashes might not be endings at all, but the long-delayed echoes of beginnings we're only now learning to see. The hierarchy problem is one of physics' most frustrating puzzles. Why does gravity seem laughably weak compared to the other fundamental forces? Electromagnetism can make your hair stand on end. The strong force binds atomic nuclei against incredible repulsion, yet gravity struggles to keep a fridge magnet stuck to the door. The math suggests these forces should be closer in strength, yet gravity trails behind by a factor of 1 trillion. This cosmic imbalance might not be random primordial black holes, could be the missing gravitational anchors that explain why our universe's forces stack up so unevenly. Picture gravity in the early universe not as a feeble background player, but as an equal contender in a four-way tug of war. Something must have happened to suppress its influence while letting the other forces dominate. Here's where primordial black holes enter as cosmic referees. If these ancient objects formed during a symmetry-breaking phase transition when the fundamental forces separated, their sheer gravitational presence might have warped the quantum fields that govern force strength. Imagine a frozen lake developing cracks as temperatures drop. Primordial black holes could be the cracks where gravity leaked out of equilibrium, diluting its apparent strength at macroscopic scales while particle-scale forces remained intense. The numbers get even more intriguing when you consider scale. Primordial black holes spanning a specific mass range, say between an asteroid and a moon, would have event horizons comparable to the scales where quantum gravity effects become significant. Their gravitational fields might act like filters, absorbing or scattering the hypothetical gravitons that mediate gravity at the quantum level. Normally, gravitons should be as abundant as photons, but if early black holes effectively trapped them in certain energy bands, it would leave gravity appearing weaker at larger distances. It's like trying to fill a bucket from a hose wrapped in mesh. Only a fraction of the water gets through, making the stream seem feeble compared to unfiltered forces. This theory flips conventional thinking about the hierarchy problem. Instead of asking why gravity is weak, we might be asking the wrong question. what if gravity isn't weak at all but concentrated? Primordial black holes could be gravitational sponges, soaking up a significant portion of the universe's curvature at microscopic scales. The gravity we measure today would be the leftover residue, like catching only the faintest hum of a distant orchestra while most of the music stays trapped in the concert hall. Some models suggest these black holes might even screen gravity in specific regions through mechanisms similar to the chameleon field theory, where gravitational strength depends on local density. The smoking gun could come from particle colliders. If primordial black holes altered the hierarchy, they might have left imprints in the mass spectrum of the Higgs boson or other particles. Upgrades to the Large Hadron Collider could detect subtle anomalies in how particles interact with gravity at high energies deviations that align with predictions of early universe black hole distributions. Even more tantalizing are proposals that certain gravitational wave frequencies, if ever detected, might carry oscillations matching the resonant frequencies of these hypothetical gravitational filters. Critics argue that introducing primordial black holes merely shifts the hierarchy problem rather than solving it. We'd still need to explain why they formed with precise masses to trigger this effect. But that's where cosmic inflation comes in. If these black holes emerged from inflationary quantum fluctuations, their mass distribution would naturally cluster around scales where gravity decoupled from other forces. The universe might not be finely tuned. It could simply be exhibiting gravitational camouflage, with primordial black holes hiding the full strength of nature's most pervasive force. Every unexplained gap in our understanding of gravity's weakness might not be a flaw in physics, but a clue pointing to dark relics lurking in the cosmic shadows since the first trillionth of a second. The cosmic microwave background is often called the universe's baby picture, a snapshot of the cosmos just 380,000 years after the Big Bang, when photons first broke free to travel through space. This ancient light forms a nearly uniform glow across the sky, but if you look closely, there are subtle imperfections, tiny temperature fluctuations that reveal the seeds of future galaxies. Yet some of these anomalies defy conventional explanations: cold spots stretching across vast distances, odd asymmetries in radiation patterns, and strange circular features that don't fit predictions. What if these cosmic wrinkles aren't random noise, but fossilized imprints left by primordial black holes lurking in the universe's infancy? Take the infamous cold spot, a region in the SIMB unusually frigid compared to its surroundings. Stretching nearly 1 billion light-years wide, this anomaly has puzzled astronomers for decades. Traditional explanations, like a colossal void in the cosmic web, struggle to account for its sheer scale and temperature profile. But primordial black holes offer an elegant alternative. Imagine one of these ancient gravitational traps forming in the universe's first moments, its intense gravity creating a localized dent in space-time. As the cosmos expanded, this distortion would have stretched into a vast depression, subtly cooling photons passing through it. The result, a permanent chill etched into the CMB, like a fingerprint pressed into cosmic clay before it hardened. The timing is critical. Primordial black holes forming before the CMB's release would have had ample opportunity to warp the surrounding plasma. Their gravitational pull would have attracted matter slightly faster than neighboring regions, creating dense shells of gas and dark matter. When photons finally decoupled, these shells would have left distinct signatures, circular shadows, in the CMB where radiation appears slightly dimmer or cooler. Some researchers argue that certain concentric patterns in the microwave background, like those observed in the WMAP and Planck data, align suspiciously well with predictions of early black hole gravitational lensing. It's as if the universe left behind a gravitational paper trail, encoded in the very first light it ever emitted. Even more compelling are the statistical anomalies. The CMB's fluctuations should follow a predictable pattern called Gaussian randomness, like static on an old television. but measurements reveal unexpected correlations between distant points, as if something were orchestrating temperature variations across vast scales. Primordial black holes could explain this through their unique clustering behavior. If these objects formed in interconnected networks during cosmic inflation, their collective gravitational influence might have synchronized CMB fluctuations in ways that mimic coordinated design. The irony is delicious. What appears as cosmic fine-tuning might actually be the aftermath of countless black holes strewn chaotically across the newborn universe. Critics counter that such imprints would require an implausibly high density of primordial black holes, but here's where quantum physics offers a loophole. If these black holes formed during a phase transition in the early universe, a moment when the fundamental forces split apart, their distribution wouldn't need to be uniform. They might have concentrated along defects in space-time, like cracks in cooling glass, leaving targeted imprints on the CMB without overpopulating the cosmos. Simulations show this scenario could reproduce the cold spot and other anomalies without violating observed dark matter constraints, making it a tantalizing tightrope walk between theory and observation. The stakes couldn't be higher. If primordial black holes did sculpt these CMB quirks, they'd offer a direct window into physics at energies a trillion times beyond what particle colliders can reach. Future telescopes like the Simons Observatory or CMB-S4 will map the microwave background with unprecedented precision, hunting for the telltale lensing patterns or polarization twists that betray a black hole's touch. Even more tantalizing, certain anomalies might encode the masses of these ancient objects, letting us weigh black holes that formed before the first stars ever ignited. Every unexplained ripple in the universe's oldest light could be a whisper from the dawn of time, a message carved in gravity, waiting 14 billion years to be read. Dark matter doesn't just hide in the shadows, it might be burning up in them. Imagine invisible particles swarming around ancient gravitational traps, colliding with such violence that they obliterate each other in flashes of energy we could detect across the cosmos. This isn't science fiction, it's a serious proposal that primordial black holes could act as cosmic furnaces, turning the universe's most elusive substance into observable light. Here's how it works. Most dark matter theories suggest it's made of particles that barely interact with normal matter except through gravity. But if these particles are their own antimatter counterparts, meaning a dark matter particle meeting its twin would annihilate, then regions of intense gravity become natural collision chambers. Primordial black holes, with their steep gravitational wells, would funnel dark matter toward their event horizons like water spiraling down a drain. As the particles pile up, their density skyrockets, increasing the odds of mutual annihilation. The result: gamma rays, neutrinos, or even exotic particles bursting forth from the darkness, a beacon signaling where invisible matter meets its end. The math behind this is as elegant as it is explosive. Dark matter particles orbiting a black hole wouldn't just fall in, they'd form a dense spike in the density distribution, crowding so tightly near the event horizon that collisions become inevitable. Some models predict annihilation rates 1 billion times higher near primordial black holes compared to anywhere else in the galaxy. This isn't just a subtle effect, it could outshine entire stars in certain energy bands, creating unique spectral signatures that telescopes like Fermi or the upcoming Cherenkov telescope array might spot. But here's the twist: these signals wouldn't look like anything else in space. Annihilations near black holes would produce particles with bizarre energy distributions, some accelerated to near light speed by the black hole's gravity, others twisted by the warped spacetime around it. Imagine a firework where some sparks fly straight up while others curve unnaturally mid-air. That's what detectors might see: gamma rays with energies too high to come from pulsars, or neutrinos arriving from regions with no visible matter to explain them. The implications ripple across astrophysics. If dark matter annihilates preferentially around primordial black holes, it would solve two puzzles at once. Why we haven't detected dark matter particles directly, they're mostly burning up near these unseen gravitational traps, and why some gamma-ray sources defy classification. Take the galactic center gamma-ray excess, a mysterious glow from the Milky Way's core that resembles dark matter annihilation signals, yet doesn't quite fit predictions. If countless primordial black holes lurk there, their combined annihilation zones could produce exactly this kind of diffuse emission, like a field of invisible bonfires glowing in unison. Critics argue that this requires too many finely tuned parameters: the right dark matter mass, the right annihilation cross-section, the right black hole density. But nature has a habit of exploiting every possible niche. If even a fraction of dark matter annihilates this way, it would mean we're surrounded by invisible particle accelerators, each one a relic from the universe's first moments, silently turning the cosmos's missing mass into light. Every unexplained high-energy photon could be a death certificate for dark matter, and a birth announcement for a new chapter in our understanding of the universe's hidden architecture. The depths of a primordial black hole might hide more than just crushed atoms. They could be cosmic alchemists, forging forms of matter so bizarre they defy the very laws of physics as we know them. Picture the unfathomable pressures near these ancient event horizons, where conditions rival those of the Big Bang itself, and particles are squeezed into states that shouldn't exist anywhere else in the universe. Among the most tantalizing possibilities is the creation of Strangelet's hypothetical nuggets of strange matter, where up and down quarks are joined by their exotic cousin, the strange quark. These ultra-dense specks would be more stable than any known atomic nucleus, turning everything they touch into identical strange matter upon contact. If primordial black holes formed during the quark-gluon plasma era, when these exotic particles roamed freely, they might have captured and compressed strange matter in their cores, preserving it like insects in amber. As these black holes evaporated via Hawking radiation, they could occasionally spit out Strangelet shrapnel, sending indestructible, self-replicating fragments hurtling through space. The terrifying beauty of this theory: a single Strangelet striking a neutron star could theoretically convert it entirely into strange matter in a chain reaction, rewriting an entire stellar remnants composition in moments. Telescopes might have already glimpsed the aftermath. Certain supernova remnants glow with energy signatures that don't match any known atomic transitions, as if their debris is cooling through states of matter we've never catalogued. But Strangelets are just the beginning. Quantum field theory suggests that the vacuum near a black hole's event horizon isn't empty. It's a frothing sea of virtual particles, including ones with negative energy. Under normal circumstances, these particles annihilate instantaneously, but a primordial black hole's extreme space-time curvature could trap them, creating pockets of exotic matter that defy intuition. Negative energy matter wouldn't just hover harmlessly. It could theoretically stabilize wormholes or warp space-time into Alcubierre-like drives, enabling faster-than-light travel. The irony is staggering. The universe's most destructive objects might secretly harbor the ingredients for interstellar highways. The most radical proposals come from string theory, where extra dimensions could allow primordial black holes to produce brain-world matter particles tethered to higher dimensional membranes that leak gravity into our universe. These wouldn't behave like normal particles. They might ignore our fundamental forces entirely, responding only to gravitational tugs from hidden dimensions. If such matter occasionally escaped during black hole mergers, it could explain anomalies like certain ultra-high-energy cosmic rays that punch through our atmosphere with no known origin. Critics argue that exotic matter remains purely hypothetical, but that's exactly what makes primordial black holes such compelling catalysts. Their formation during the universe's most extreme epoch means they could have briefly accessed energies and states permanently lost to the cooling cosmos. Every unexplained high-energy event, every bizarre particle detection, might be a breadcrumb leading back to these ancient crucibles where the rules of reality itself were still being written. And if we ever confirm their role, it would mean black holes aren't just cosmic dead ends, they're laboratories, forging materials beyond our wildest imagination since the dawn of time. The universe's final act might not be the silent fade out we've imagined. It could be a dramatic encore staged by primordial black holes. Long after the last stars gutter out and galaxies drift apart, these ancient gravitational relics could become the cosmos's last active players, reshaping reality in ways that challenge our bleakest predictions. While most theories of cosmic fate focus on heat death, a cold, endless expansion into darkness, primordial black holes introduce wild cards that could rewrite the script entirely. Take the traditional heat death scenario first. As space expands, matter thins until atoms are spread so far apart that the universe becomes a near-perfect void, with temperatures approaching absolute zero. But that's assuming nothing intervenes. Primordial black holes, especially the smallest ones, would still be evaporating via Hawking radiation at this late stage, their final moments releasing bursts of energy into the void. Picture a near-frozen cosmos dotted with countless microscopic fireworks, each explosion briefly reigniting tiny pockets of space with heat and light. It wouldn't stop the inevitable, but it would add a stunning counterpoint to the silence, like embers flaring in a dying campfire. Now for the twist. If enough of these black holes survive into the far future, their collective evaporation could trigger a phase transition, a fundamental shift in the fabric of reality itself. Quantum field theory suggests that our universe's vacuum state might not be the lowest possible energy configuration. A sufficiently energetic event, like the simultaneous evaporation of trillions of primordial black holes, could punch space-time into a lower energy state, rewriting the laws of physics in an instant. The result, a new Big Bang emerging from the ashes of the old universe, with primordial black holes acting as cosmic seeds for the next cycle. It's not heat death, but a cosmic reboot, one where the remnants of our universe become the raw materials for another. But there's an even stranger possibility. If primordial black holes are connected to extra dimensions or hidden sectors of physics, as some string theory models suggest, their evaporation might not just release energy, but information. The data locked behind their event horizons could cascade into the vacuum like a computer code executing, reprogramming the fundamental constants of nature. Gravity's strength, the speed of light, even the mass of electrons might shuffle into new configurations, birthing a universe unrecognizable from our own. In this scenario, primordial black holes aren't just relics, they're cosmic programmers. Their demise a line of code that launches the next simulation. The ultimate irony, these black holes, often dismissed as dark, destructive anomalies, might be the key to cosmic immortality. While stars burn out and matter decays, primordial black holes could endure long enough to bridge the gap between universes, carrying forward subtle imprints of our cosmos into the next. Every gravitational wave they emitted, every particle they swallowed, might echo in some future reality, a whisper from a universe that refused to die quietly. And if that's true, then the darkest objects in existence could also be the universe's most stubborn survivors, outlasting time itself to shape whatever comes after. From dark matter architects to cosmic time capsules, multiverse messengers to quantum entanglement hubs, primordial black holes have taken us on a journey that bends the very fabric of reality. These ancient gravitational ghosts don't just lurk in the shadows of our universe. They rewrite the rules of physics, offering wild solutions to mysteries that have puzzled scientists for generations. Imagine objects so dense they could be hiding inside planets, so stealthy they might form the invisible scaffolding of galaxies, or so strange they could be pulsing with the heartbeat of a parallel universe. Each theory peels back another layer of cosmic truth, revealing how these relics from the dawn of time might hold the keys to everything from dark energy's grip on the cosmos to the fate of reality itself. What makes these theories so thrilling isn't just their audacity, it's the way they force us to rethink the fundamentals. Gravity, time, even the nature of matter itself take on new meaning when viewed through the lens of primordial black holes. Could they be the missing link between quantum mechanics and general relativity? The answer might lie in their evaporating whispers or the echoes of their collisions. They challenge us to consider whether black holes are cosmic endpoints or something far more dynamic, wormholes to other dimensions, factories for exotic matter, or even seeds for new universes. Every unexplained gamma-ray burst, every anomalous gravitational wave could be a clue pointing toward their shadowy influence, but the most exciting part. This isn't just theoretical musing, it's a detective story unfolding in real time. Telescopes scan the skies for flashes that might betray an evaporating black hole's last gasp. Gravitational wave detectors listen for the chirps of ancient collisions. Particle accelerators hunt for remnants of quantum gravity. With every new discovery, we're piecing together a puzzle that stretches back to the first moments of existence. And whether these black holes turn out to be dark matter, time crystals, or something beyond our current imagination, one thing is certain: they're proof that the universe is stranger, richer, and more interconnected than we ever dreamed. So what's your take? Which theory bends your mind the most? The idea that primordial black holes might be hiding in our solar system, or that they could be fossils from a previous cosmos? Drop your favorites in the comments below, and don't forget to hit subscribe for more deep dives into the universe's greatest mysteries. The cosmos has kept these secrets for billions of years, but the next revelation could be just one observation away, and you won't want to miss it.